Good day everyone. The assigned hands-on application under the topic relativity is I will going to contact my grandma and explain how Einstein's theories of relativity concern the fast and the big, that relativity is not only out there but also affects this world. Tell her how these ideas stimulate your quest for more knowledge about the universe. Impress grandma by properly using the words there, and there in your explanation. So, in order to contact my grandma, I send a video of myself discussing the Einstein theory of relativity. Hi grandma, good day. So now I'm going to explain about the Einstein theory of relativity and its effects to this world. So first, this theory explains the behavior of objects in space and time, and it can be used to predict everything from the existence of the black holes to light bending due to gravity and the behavior of the planet and Mercury in its orbit. So his work transformed our way of living in the cosmos. When Einstein put forward his general theory of relativity, that gravity itself is the beginning or bending of space and time by mass and energy. There was a seminal moment in the history of science. Today, the importance of his work is even better recognized than a century ago. Relativity tells us that the same laws of nature hold true everywhere in the universe. This equivalence principle also confirms that two bodies fall through a gravitational field at the same rate regardless of their mass. By studying the cosmos beyond our own planet, we can understand where we came from, where we are going, and how physics works under conditions which are impossible to recreate on Earth. So, there are examples that general relativity to work and may help their understanding to manipulate in mind about that concept. And there are effects that can be seen in our everyday lives and govern everything from GPS system to the electricity that powers our homes. The GPS devices work by calculating a position based on communication with at least three satellites in its distance. Earth orbits. Those satellites have to keep track of incredibly precise time in order to pinpoint a location on the planet, so they work based on atomic clocks. Another example is the black holes are one of the few places where both general relativity and quantum theory should apply. Relativity because of their massive space warping capability of the dead star, and quantum physics because of their infinitely small size of the singularity at the center of the black hole. So everything in the universe is traveling through space-time and the speed of light and the maximum speed possible, and if they are sitting still in space, then they are traveling through time at the maximum speed. But if they begin traveling through space, then their progress through time slows down. So that's all, and I'll send you more information next time.
You can't see it, you can't hear it, you can't weigh it, but we experience it every moment. The whole piece of time is a landscape, and we move through it, slice by slice. But do we really understand time? Is time same for everyone? To understand time, let's go back in time and make a small journey with a certain young patent clerk, Albert Einstein. Imagine you're traveling with Einstein in a train moving at a certain uniform speed. The train, relative to the outside environment, is in motion. The two of you sitting inside, on the other hand, observe each other as stationary objects, as both you and the train are moving at the same speed. Hence, relative to the train, you are stationary, and the laws of physics stay same inside the train as they would on the ground when you are standing still. Now let's consider you get off the train and observe it moving across in front of you. Now you are stationary and relative to you, Einstein is moving with the same speed as the train. This is the phenomenon of relative motion, and we observe it every day. Does everything in the universe observe this relative motion the same way? Yes, everything except light. Light behaves in a different way. Imagine you have a light clock with you. This light clock has two mirrors in the opposite directions and a light beam bouncing between them. Now, let's say the distance between the two mirrors is d, and the time for the light to cover that distance is t. For the sake of simplicity, let's say it's 1 second. So, when this clock is with you at rest position, the light bounces between the mirrors, covering distance d in 1 second, which gives us the speed of light s. Now remember, speed is distance per unit time. Now consider Einstein also possesses the same light clock with him. Only this time, he's traveling in a spaceship along with the clock. When Einstein travels in a certain speed, the clock travels with the same speed of the spaceship in the same direction. Here, light has to travel an extra distance in the same 1 second. Let's consider this distance to be capital D and represent the speed of light here as capital S, which has to be greater than small s. But something's wrong here. Because in the late 1800s, the Michelson-Morley experiment tried to detect the relative motion of the matter through an ether and concluded that the speed of light is constant. This cosmic speed limit is known as c. So in our little scenario, small s and capital S are equal. So for the speed of light for both you and Einstein to remain constant, something has to give way. That something is time. It turns out, time slows down when you travel faster and faster, nearing the speed of light. So the faster Einstein travels, slower the time passes for him. Hence, what could be a day for Einstein in space could be as much as 50 years for you on the ground. This became the fundamental